And welcome to today's lesson. In this tutorial, we will be able to solve trigonometric equations for all values. So we're in section 6.7 in our textbook, and we're going to be changing gears a little bit and now talking about trig equations as opposed to the identities that we've been working with. Remember, identities work for every single value. Trig equations will only work for some values, and our objective, of course, is to find those values. Unlike the identities where we were restricted to working only on one side, we can use whatever algebraic techniques we have to solve. We can deal with both sides. We can factor, which is what we're going to be looking at in these first two examples. We can add, subtract, multiply, divide by whatever we want to both sides. We can gather our like terms together. All of the techniques that we've been using to solve equations in algebra, we can use with our trig equations as well. Before we get started with trig, I'd like to review a couple examples from Algebra 2 or from Algebra 1. These are some quadratic equations. I know that they're quadratic because we see the little x squared. That means that there will be two solutions to these equations. When we have quadratic equations, usually we like to set them equal to 0 and factor them to solve. If they can't factor, we could use quadratic formula, but I'm going to try factoring first. This one is already ready to go. It's in standard form and it's set equal to 0. I factor trinomials using trial and error. I split apart the first term into its possible factors. I split apart the last term into its possible factors. Since there's only one set of possible factors for the front, I'm going to put the 3x and the 1x in the front of my parentheses, in the front of my factors. The 1 and the 2 are the only options here, so they will go in the back of the parentheses, but I don't know if it's a 1 and a 2 or maybe a 2 and a 1. I do need to use the middle term now to check to make sure that I'm correct. It needs to be a 1x. If I put the 2 here, then the 2 times 3x becomes 6x. And the 6x and the 1x are not going to be able to make this 1x. So I know that the 2 is probably going to go here and the 1's going to go here. The negative 2, this negative sign means that I must have alternating signs, because if I'm going to multiply to get a negative 2, then one has to be positive and one has to be negative. If I put the positive here and the negative here, let's check my, my inner and outer terms. My 3x times my 1 gives me 3x. My negative 2 times x gives me negative 2x. That adds up to positive 1x. Now I know that I've factored this correctly. Okay, once you have your two factors, again, it's equal to 0, so please make sure that it's an equation in every step of the way. Please do not forget equal to 0 right here. Once you have two factors multiplying together to equal 0, you can set each one equal to 0, and in this case, positive 2/3 will be the solution, and in this factor, negative 1 will be the solution. So that's solving by factoring. I want to show you this second one so that you don't make the mistake that some people make. They like to think that they could just divide by x here. And I'm going to make a quick note here. Never divide by your variable. You should never divide by your variable, at least not the variable that you're trying to solve for. If you have the urge to divide by a variable, it's most likely because it's a GCF. Now, it might not be a greatest common factor yet until both terms or all the terms are onto one side, but that's what we need to do. This is quadratic. We should set it equal to 0 and factor. If I subtract the 4x, I'll have x squared minus 4x equals to 0, and then I can see that there is a common factor that is shared. I can pull that factor out as a GCF and be left with x minus 4. And then that's the simplest way to factor something, just pulling out a GCF. Now I've got my two factors, x equals 0 and x equals 4. And I have my two solutions. Now, the people that tried to divide by x right from the beginning would get one of the solutions, x equals 4, but they'd miss out on the second solution. And since that second solution is 0, what they tried to do is divide by 0. And we know that we can never divide by 0. So please never divide by your variable, never divide by your trig symbols that you see in today's equations. Set it equal to 0 and factor. Okay, let's look at our first trig equation. Part A says we have 2 sine x minus 1 is equal to 0. I know that I'm ultimately trying to find x, but before I find x, I'm going to get sine of x to be all by itself. So to get sine of x, I'm going to treat sine of x as the variable. I'm going to add 1, and I'm going to divide by 2, so I'll have sine of x is equal to 1/2. Now we are looking for all possible values, not just unit circle values, all possible values. So we'll talk about that when we get there. It does feel good to have the sine equal to 1/2 because that's one of our special unit circle values. And most of the time we're going to have that. I'm going to draw a picture of the unit circle, or perhaps you have your unit circle next to you right now. I want to know, when is the sine equal to 1/2? Well, the sine travels up and down. The sine is the y. So when I go up 1/2, I know that's up because it's positive. I know that it's going to be this angle or this angle that get me to go up just the little 1/2. Now, this is not like the inverse trig that we've already learned, where we just pick one value. I'm looking for all possible values. So right now I have this one, which is pi over 6, and this one, which is 5 pi over 6. That's 2 of my infinite answers. Please understand that pi over 6 is not the only answer. We could wrap around the unit circle again and say 13 pi over 6, or wrap around 2 times and say 25 pi over 6. There are infinite answers. So what we're going to say is, yes, x can equal pi over 6, but we're going to add a multiple of 2 pi to that answer, because this means that we can wrap around the unit circle however many times we want. And remember, k is just representing an integer. If k is 0, then I'm talking about the original pi over 6. If k is 1, then I'm talking about wrapping around the circle one more time. Or if k is -1, then I'm wrapping around the circle in the negative direction. The other answer is 5 pi over 6. And of course, I can continue to add 2 pi to that as long as I want to. So I'm going to add 2 pi k to that. So those are my answers for my first one. The second one, again, I'm looking for x, but before I find x, I want to get 2x by itself. And before I do that, I want to get cosine of 2x by itself. So what I'm going to do here, since I see that there's going to be a term I can add to the other side, I'm going to add cosine of 2x to both sides. If I add cosine of 2x to both sides, that's fine. I have some like terms. That's gone. And now I have 2 cosine of 2x. That's fine. At the same time, I think I'm going to subtract my square root of 2 to the other side. And I'll have this is equal to negative square root of 2. Remember what I'm trying to do. I'm trying to get cosine to be all by itself. So since there's still a 2 there, I'm going to divide by that 2. And I'll have cosine of 2x is equal to negative square root of 2 over 2. That feels like a good value because that's one from the unit circle. Now, I know that we've dealt with double angles before, and this is a double angle, but that's fine. We don't need to use an identity here. We can get rid of the cosine just by looking at the unit circle and figuring out what angles we're talking about. So don't worry that this is a 2x as opposed to the 1x that was over here. We can deal with that once we look at our unit circle. So I'm going to draw a picture of the unit circle again. I like to visualize that. If I'm talking cosine, this time I'm talking left and right. And if I'm talking left or right, I need to know which direction. Oh, it's negative, so that means we're going to the left. The cosine forcing me to go to the left, negative square root of 2 over 2, would be this middle angle here and this middle angle here. And those are the two angles, at least in the unit circle, that have a cosine that's equal to negative square root of 2 over 2. This is not the answer yet because this is just what 2x will be equal to. This angle is 3 pi over 4, and the other one is, this other angle is 5 pi over 4. Obviously, you still need knowledge of that unit circle. Now, again, what we can do is we can add 2 pi to each one of these and continually get to other ones. So I'm going to add my 2 pi k to each of these. Now, if this were just cosine of 1x, equals to this, we would be finished. But because we still have 2x, we need to get rid of this 2. And getting rid of this 2, a lot of people want to just divide by 2. I'm going to multiply by a half because I know that I'm dealing with a fraction here on this side. And I have to multiply all parts by 1/2. I'm multiplying by a half because I think that's easier to deal with the fractions. The 1/2 times the 2, of course, cancels out, and now I'm going to have my two answers. X is going to be equal to, this is 3 pi times 1 divided by 4 times 2. So this is 3 pi over 8. And half times 2 pi k would just be 1 pi k. My second set of answers, 5 pi times 1 and 4 times 2 gives me 5 pi over 8. And then the same thing happens here. 2 pi k cut in half would be 1 pi k. So if you happen to have a multiple angle in the original part of your problem, that's okay. You're just going to be either dividing by that coefficient or multiplying by its reciprocal. Just don't forget your pi k's and your 2 pi k's. Let's look at another problem. Let's look at example C. This time we're looking at a tangent, and I know that it's a tangent squared, so you might think maybe we're going to be factoring in this case, but because there are only just the two terms and I don't have the linear term, I'm not going to factor. I'm just going to set tangent squared. I'm going to solve for tangent squared, and then I'll just take square roots. That's the easier way to get rid of this squared right now. I'm going to add 1 and divide by 3 and isolate the tangent squared. And that will be equal to 1/3. And then I will just take the square roots. I'm okay taking the square root of both sides of an equation as long as I remember that I'm taking plus or minus this other side. When you put a square root symbol on, when you put it into the equation, then you have to make sure that you're taking plus or minus both roots. The square root of tangent squared, of course, just becomes tangent. And the square root of 1/3, well, I'm going to split it up into the square root of 1 and the square root of 3. Now, it's no good to have that square root of 3 there, so we're going to rationalize, and rationalizing is not too bad. Most people can just do it in their head. I'll show the work here. We're multiplying by the square root of 3 over the square root of 3, and we get that the tangent of x is going to be plus or minus the square root of 3 over 3. And that rings a bell from our unit circle. That's quite helpful. Draw my unit circle. I need to remember when the tangent is equal to the square root of 3 over 3. And my little trick to remembering that, if I see two 3's, then I know I'm talking about the pi over 6 angles. And the positive square root of 3 over 3 would occur at this pi over 6 and this pi over 6. The negative square root of 3 over 3 would occur at this pi over 6 and this pi over 6. So we got our little cat whiskers going here. All 4 of these are the answers, at least in the unit circle. But if I'm looking for all possible values, I still have some work to do. Now, some people will answer this with 4 different answers. They'll say pi over 6 plus 2 pi k, 5 pi over 6 plus 2 pi k, 7 pi over 6 plus 2 pi k, and 11 pi over 6 plus 2 pi k. And that would be the answer. That's absolutely fine. But what I'm going to do is be a little bit more efficient. I know that pi over 6 is exactly 180 degrees away from 7 pi over 6. Or in terms of radians, it's exactly pi away. So if I add pi to this angle, I will get exactly here, which is one of the other answers. And if I continue to add pi, I will keep bouncing back and forth from these two angles. So I could just say pi over 6 plus pi k, and understand that that will get both of these angles and all of the other ones back and forth, back and forth, back and forth. I still have another set of answers, and I'll pick the 5 pi over 6. And I know that 5 pi over 6 is exactly pi units away from the 11 pi over 6. So I can just say 5 pi over 6 and add pi k to that. That's the most efficient way to write this answer. But like I said, you could write it as 4 separate things and add 2 pi k to each of them, and you'd still have the same correct answer. This is maybe just a little bit more efficient. Some people say pi over 6 plus pi k and negative pi over 6 plus pi k. That's fine, as long as you're writing in an expression for all possible values, you've got the answer. So there's a good tangent problem. Let's look at part D. Oh boy. This one's a little bit different from the other ones that we've seen because now they're technically, I know there's only one variable, it's just an x, but I see really that there are 2 functions on that variable. I see a cotangent of x and I see a cosine of x. It's sort of like 2 different variables, and that's tough to deal with. We can use our trig identities and substitute something out if we wanted to, but I don't really see anything that's going to help us. I know that cotangent is cosine over sine, and then I'd have another cosine, but I'd still have a second function called the sine. Some people might say, wait a minute, there's a cotangent on both sides. Why don't we divide by cotangent? Well, like I said in the first slide, that's a big no-no. Never divide by your variable. If you have the urge to divide by your variable, it's because there's an eventual GCF. And that gives me a clue as to what I'm going to do. I'm going to subtract 2 cotangent x from both sides. I'm going to set it equal to 0, and I'm going to factor out that GCF. Now this term and the term that I just subtracted, they are not like terms, so I will just write these side by side. Cotangent times cosine squared minus 2 cotangent. Set it equal to 0. Now I can see that they share this common factor of cotangent, and I'm going to factor out the cotangent common factor. If I factor out cotangent, I'm left with cosine squared minus 2. So once it's in factored form, set equal to 0, I can set each factor equal to 0. And now it doesn't matter that I have 2 different functions because each one can be separated at this point. I'm going to set cosine squared, I'm going to add 2, equal to 2. So now I have 2 equations to solve. Let's solve this first one. Cotangent equal to 0. Not many people memorize their cotangent values, but I do know that cotangent is cosine divided by sine. So if I'm talking about cosine divided by sine equal to 0, I'm really talking about when is that numerator equal to 0. So really I'm solving this equation because a fraction is going to be equal to 0 when its numerator is equal to 0. So let's see what we've got. Let me draw my picture. Again, you might just be looking at a picture. I like to draw my picture each time. If I want to know when is the cosine equal to 0, that means when I go left or right, I actually don't go left or right. And the 2 angles that will force me not to go left or right are the top and bottom of my unit circle. So here is pi over 2, and here is 3 pi over 2. Now you can say pi over 2 plus 2 pi k, and 3 pi over 2 plus 2 pi k, or for the same reasons we talked about over here, since they are exactly symmetrical around the unit circle, I could just pick one of them and add pi k to it, and it'll bounce to the bottom one, and then back up, and then back down, and then back up, and then back down, and you can see that those will be the answers from this. Okay, we have some work to do over here, or so we think. We're going to take the square root of both sides, as long as we remember plus or minus. And we have the cosine is equal to plus or minus the square root of 2. Now this does not really ring a bell for me. I don't remember when the cosine equals square root of 2 in the unit circle. In fact, square root of 2 is a number that's bigger than 1. Negative square root of 2 is a number that's less than negative 1. The biggest that the cosine could possibly be, the biggest that the cosine could possibly be is 1. We can't get out here to square root of 2. So this doesn't even make any sense, and there aren't going to be any solutions from this branch. We thought there might have been, but there aren't. The cosine, the biggest it could possibly be is 1, and square root of 2, of course, is bigger than square root of 1. So therefore, there are no answers here, and these must be the only answers for this problem. Sometimes that'll happen. You'll get some nonsense over here, and just say that there's nothing from there, and just circle what is the correct answer. Okay, we're getting into it here. Two more examples here. This is part E. I'm looking at this one. Good news is we're back to just one function. It's just the sine. Tough news is we are going to have to factor this one. But that's okay. We've factored with trig before. I know that this is quadratic, and this time the linear term is there. So setting it equal to something and taking square roots will not be a good strategy in this case. I need to factor this. I know that there's only one option for the front. That's 2 sine times 1 sine. And there's only one option for the back. In fact, it can only be 1 times 1. So that's not too bad. I know that the 2 sine and the 1 sine will be in the front of the parentheses. I'm still setting it equal to 0 here, of course. And the 1 and the 1 have to be in the back. Okay, that's not too bad. And they have to have alternating SIGNs, right? Alternating signs. SIGN. So I need a positive and a negative, and it needs to be a negative sign in the middle. So if I put the negative here and the positive here, that's actually going to do it. So 2 sine times negative 1 makes negative 2 sine, and then add the 1 makes the negative 1 sine. So that's good. So this factor, sine, could be equal to subtract 1 and divide by 2, negative 1/2. And this factor, sine, could be equal to add 1, 1. Nice unit circle values here at the negative 1/2 and the positive 1. I like that. Let's draw the unit circle. Actually, I'm going to just draw it in the middle so I can use it for both of these. Let's talk about sine again. We're talking sine is negative 1/2. That's down. That's down just a little bit. That must be here and here. These are the two angles where the sine would be negative 1/2. Look on your unit circle. Now these are not exactly symmetrical. So there's no way of naming one and adding something to it to get to the other one that's the same thing to add to get back. So I do have to use two separate statements here. I have to. So x is equal to, I'll call this one 7 pi over 6. And I'm going to add 2 pi k to it. And this one I'm going to call 11 pi over 6. You might choose 11 pi over 6. You might choose negative pi over 6. It doesn't really matter. Some people are used to the inverse trig where you use the faster way of calling that. I'm just going to use the unit circle values that we've memorized, the ones between 0 pi and 2 pi. So those are those two. Let's see what else we've got. Sine can also be equal to 1. And the sine equaling 1 happens way up here, which is pi over 2. And that's the only one. So pi over 2 plus 2 pi k, and we'll be done here. Pi over 2 plus 2 pi k. Remember, we're looking for all possible values. That's why we keep adding the 2 pi k to all of things, unless we can find a more efficient way. Good job there. Let's look at E and compare it to F. E was a factor problem. F looks like the same type of problem, except we have two different functions. We have a sine on the x, and we have a cosine on the x. And that is not going to be factorable because it's technically two different functions. So it's like two different variables. So we can't factor this yet until we do something. Now, we have our identities at our disposal, and we do know that we have a name for sine squared. There's not much that we can do with cosine to try to get cosine to turn into sine. In fact, it's impossible. But there is something we can do with sine squared to turn that into cosines. Sine squared is 1 minus cosine squared. I'm going to replace the sine squared with 1 minus cosine squared. That's one of our Pythagorean identities. And that one step gives me an equation that only deals with cosine. We have some algebra to do first. We can distribute, and we'll have 2 minus 2 cosine squared. And then we can gather our like terms together. I see the I see the 2 and the -3. I'm going to put my quadratic term first, the -2 cosine squared, and then the linear term 3 cosine, and then 2 and -3 make -1. I know that I'm going to be factoring this because I have a quadratic, or at least a quadratic form, but I don't like that the leading term is negative. So if you don't mind, I'm going to divide everything by -1 to make this term a positive 2 cosine squared. This term would then turn to a negative, and this term would then turn to a positive. 0 stays 0. I like to factor with leading terms that are positive. So I've got 2 cosine times 1 cosine. I've got 1 times 1. So the front of the parentheses will have the 2 cosine and the 1 cosine. Whoops, I almost did a sign. And the back of the parentheses will have a 1 and a 1. This time, since it's a positive one, both of the SIGNs have to be the same, and this tells me what they both have to be. They'll both be minuses. So that's good. I've got my 2 factors. So this factor, cosine, could be equal to 1/2. That feels good. Positive 1, we're adding 1, and then divided by 2. 1/2 rings a bell from the unit circle. And this one, cosine, could equal to 1. Great. Let's draw a picture of our unit circle. I'm going to draw it in the middle again. Now we're talking cosine. We're going a different direction. That's left and right. If I'm talking cosine is positive 1/2, that's just the little distance to the right, and that must be this angle and this angle. Again, they're not exactly symmetrical around the unit circle, so I have to write them as 2 separate statements. That's pi over 3 plus 2 pi k. And the other one, you could call it negative pi over 3, but again, I'm just going to go with my unit circle. I'm going to call it 5 pi over 3 plus 2 pi k. So those are those 2 sets of answers. And my last answer, I have the cosine is equal to 1, and that brings me all the way out here, and that's just 0 pi. So I'm going to say 0 pi plus 2 pi k, or rather 2 pi k. I don't need 0 plus something. I can just put the something, 2 pi k. So let's look at one last situation today, and that is part G. We have the cosecant of x is equal to -2. So we don't typically memorize our reciprocal values from our unit circle. So let's deal with this cosecant. Our cosecant we know is 1 divided by the sine. So cosecant x is equal to 1 divided by the sine. So we know 1 over sine is equal to -2. And what we can do with an equation, as long as we do it to both sides, is we could take the reciprocal of one side. So if we take 1 divided by the sine and flip it upside down, we would have the sine divided by 1. But we have to do it to the other side as well. If we take -2, which is actually -2 over 1, and flip it upside down, we would have 1 divided by -2. Or if we clean this up a little bit, we have the sine of x is equal to -1/2. So when the cosecant equals -2, that's the same thing as when the sine is equal to -1/2. And now we have it. We know that the sine is equal to -1/2. Let's draw a quick picture. Down here and here. And if we're naming all of the angles, let's start with this guy right here, which is 7 pi over 6. And let's add 2 pi k to that. And we also have, I'm going to do the unit circle value again, 11 pi over 6 plus 2 pi k. And those are our answers there. We could call this negative pi over 6 and maybe even -5 pi over 6. There are a bunch of names for this. I'm just going to choose to remind myself of my unit circle values. But don't forget to add the 2 pi k so that we have all answers. So it's okay if we're dealing with one of our reciprocals. Let's just flip both sides of the equation so that we have something that we already know about. So that's part one of solving trigonometric equations. Thanks for watching this tutorial. We'll practice these techniques in class next time. Thanks for watching. See ya.